for a brief pause, siguro naman we can do it. Other than that, lecture 4 and 5 is, no, 3 and 4 is ready to go. And this is unfortunately the end of me basically having an easy reference to design PowerPoints off. So here's the thing. I'm already at the limit of what I fully know. So I'm planning na moving forward, we'll be doing group reports kung sakali. Would everyone be fine with that possibility? Also, nagpipick up ba yung noise ng fan ko? Yeah, I kind of figured. Nakikita ko kasi nagtitrigger yung mic eh. But yes, I'm planning sana moving forward na group reports kasi kulang na talaga ako sa context kung ano yung mga underlying principles. I need to stress na my background is mechanical engineering. Hindi kami talaga pumalo sa signal processing, although may parallels kami when it comes to control system design. Because what we'll be talking about today would be signal conversion, signal conversion, filters, and the sampling theorem. Ang problema, none of those except siguro for filters tinamaan sa engineering when it comes to control systems. More often than not, the experience I can draw from would be system vibrations and response. While I cannot visualize the entire thing in terms of circuitry, somehow I can visualize it in terms of physical systems that happen to have a bit of spring in them. It turns out mechanical engineers have a bit of an importance when it comes to those old school magnetic disk hard drives. Ang pakialam namin basically would be the needle and the overall rotation of the hard disk. But we're also reaching a point wherein those magnetic disks are being replaced by solid state drives. I'm also going to see what happens if I change out the fan. So let's see, baka either mag-amp up yung noise pa or mabawasan. Kahit pa paano, the air is bound to blow into my microphone. I'm trying to also see if I can avoid using the AC. So what about this one? Napipick up pa rin yung noise ng fan or di masyado? Sige. So siguro let's muna with the first two. Then we'll take a brief break while I make the last slide for the last PowerPoint. First things first, I'm going to start sharing a screen and hope that this computer doesn't die. I think I'm stretching the battery far. So yeah, limits of my understanding, and moving forward, I'm going to start breaking down the syllabus and modules to groups for reporting. That way, we'll have an even better understanding of our topics at hand. Now, with signal conversion, let's start off muna with analog to digital. So more often than not, kasi yung likely na gusto natin mangyari daw, we're able to somehow transmit those signals through and through. And more often than not, we can transmit them digitally. There are, however, studies in trying to make use of analog computers, but that's besides the point. If anything, that's beyond scope. But in trivia lang, some people are experimenting with analog computers. Hell, analog computers exist well before semiconductors. They're like mechanical and all that. So what about analog to digital conversion? Well, apparently some core concepts include sampling and quantization. Apparently, they don't always come hand in hand. Pero as I was looking into the modules for today, the cases we're dealing with are basically have those two come hand in hand. So sampling, you're basically chopping up time into discrete points. So rather than tuloy-tuloy, hinati mo siya into specific time codes. So parang this millisecond, that millisecond, and all that. And then at that point, you're now looking at it as if you're now looking at those time codes as sample points. And then comes quantization. So it's one thing na kinuha mo yung value at that point in time. Pero unfortunately, there are limitations when it comes to data handling. So porke nakuha mo na yung data at that one sample point, hindi pa siya fully quantized. At that point, you now have to force it into the data type into where you're storing it. Kumbaga, when you quantize it, you're basically storing it as a bit. And funnily enough, there's like an overlap when it comes to physics, but that's also beyond the scope of today's lecture. Quantization goes beyond digital signal processing. It's a lot more fundamental than you'd think. So apparently, the first step when it comes to signal conversion is the sample and hold step. So yun nga, as I was mentioning, the instantaneous value at that particular sample point, kunin mo. So parang ganito yung magiging transformation niya with sample and hold. Of course, the next is quantization. And at that point, that's where you start getting errors. So sabihin natin, yung na-sample mo at that moment in time was 1.01 millivolts. No, that's a bit too precise. Sabihin natin 1.01 volts. Pero yung precision, yung resolution ng device mo, kaya lang niya kada 0.2 volts. So, ano na mangyayari sa sample natin na 1.01? I mean, ano nga bang sinabi ko? Sorry, let's try that again. Let's say you got a sample of 1.1 volts, but your measuring device has a resolution of 0.2 volts. So at that point, yung nakuha niyang sample will have an error introduced into it. That 0.1 difference from between the recorded and the actual is basically that quantization error. Kumbaga parang yung resolution is associated to the least significant bit na kaya ma-handle ng device. So, yes, sir. Seemed like you were about to say something. Perhaps you have insights sa kwan ko? Or napindot lang? I'll assume napindot lang. But yes, quantization error is sort of a result of data handling, the imprecision when it comes to the resolution of your devices. Now, here's the curious thing about quantization error. More often than not, uniformly distributed siya at around half of the least significant bit, with a standard deviation of approximately 0.29 least significant digits. Unfortunately, there will be circumstances na hindi yan uubra. What happens if that happens? What happens kung magkakaganon tayo? At this point, we now have to employ a technique known as dithering. So let's say, nagkataon, lahat ng quantization errors mo, they're all above the actual value, no? So at that point, yung mangyayari sa digital signal mo, yung mas maarte dapat sana, parang na-flatline na lang siya to that one point. So ang gagawin mo, you try and somehow make use of additional noise, or at least the pre-existing noise. Somehow, ang mangyayari dyan, habang nagsisample siya along that supposed flatline kapag nalinis yung signal natin, instead, yung random noise introduced will end up being able to dislodge that signal from that flatline. So, more often than not, yung noise na nandun na, gagamitin mo na sa pag-process sa analog signal. Somehow, the noise ends up becoming self-corrective. There are, however, more complicated methods wherein the noise is artificially introduced based off of some parameters sa signal. So, bale, more complex systems, mas lalo na kapag if you have a surplus of processing power, you can go with subtractive dither. Now, yung usual na nangyari, interesting. Okay, so okay, I'm mixing this up with yung filter slides. So now that we have the entire thing digitized, let's say gusto natin pabalikin to an analog signal. This time around, we're going to try and reproduce that signal with, one approach we can do that is basically using what we call an impulse train. So kung balikan natin yung parang easy stuff with regards to our output functions. Mga step functions natin, meron tayong impulse, meron tayong step function, and meron tayong ramp function. One way or another kasi, those functions can be used in a combination to be able to reproduce the signal. More often than not, yung simpleng digital back to analog, impulse train. So bale, yung nasample natin, ganitong kalakas siya at this certain point. Parang uulitin mo lang siya, pero imbes na hold until the next sample, parang sisipain mo lang for that strong. So let's try and visualize this. What would an impulse train look like? And, okay. Apparently, hindi ko siya na, wait, no. But we're on track. So sabihin natin, we have our original analog signal. Now, it turns out, there are a few other interesting things din. It's not enough na you have amplitude versus time. One thing kasi that's critical when it comes to signal processing would be frequency. And pagdating din sa structural engineering, amplitude versus frequency is another thing we also have to worry about. Resonance basically is yung sakit ng ulo namin. We actively want to avoid that. Pero there are certain instances wherein resonance is perfectly fine. Point is, the reason why we sort of graph amplitude against frequency is to see the spectrum of the entire waveform, if you may. And well, there's an interesting little problem with regards to that, but I believe that's within the coverage of the upcoming, of the midterms exam, probably the finals. But I'm getting ahead of myself. Point is, ito yung itsura ng original analog signal natin. But what happens when we turn that into an impulse train? Well, this is sort of what it ends up looking like. Pero we also have set like a rate in which kailan tayo nag-apply ng samples based sa frequency. Now, here's the curious thing about it. That impulse train has its own spectrum, and it's not going to be a perfect match to the original spectrum. So parang mangyayari, you're going to end up introducing harmonics pagdating sa original signal. Harmonics basically are like multiples of the original frequency. So let's say, sabihin natin 1 hertz. Yung mga harmonics nun, 2, 4, 6, 8, and so on. Multiples of the 1 hertz. So we need to do something extra when it comes to this. Alternatively, kung try natin baguhin yung sample rate natin when it comes to reproducing the signal, that also creates its own curious problems then. So the impulse train approach will introduce some signal noise, which eventually becomes a problem that we will discuss much later. So pay mind to that term, aliasing. That's actually, I believe I've lumped that into the part about sampling theorem, and it should be within sampling theorem and later down the line filters then. Now, another approach when it comes to digital to analog conversion, more often than not, gagamit ng op-amps. So parang yung mangyayari, kada bit, you assign it to a particular voltage output. So one common approach apparently is the binary weighted ladder approach, wherein yung pinakamalaking bit mo, yung may pinakamalaking voltage, and then kada kasunod na bit niya, pakalahati siya ng pakalahati. So as much as it's an analog signal, mahalata mo pa rin yung pagka-digital niya when you start plotting it. So parang, voltage 4 is basically half of voltage 3, which in turn is half of voltage 2, and then eventually half of voltage 1. And yet, yung combination ng lahat ng mga voltages na yan, when you read it in a different device, parang you'll be able to reconstruct the digital signal sent its way. So, yun lang. Apparently, this example is known as an inverting summing amplifier. Now, another approach I've seen yung apparently would be the single-bit data conversion. So, there's this idea kasi na as you're able to increase the sampling rate, you need less and less bits in order to represent the signal. So, with the previous example of the 4-bit DAC, one can imagine kung ano yung sample rate nun. What more pa kung napilit ka into a single-bit DAC? That's bound to have like a crazy sampling rate when it comes to being able to produce that signal. And unfortunately, you cannot go into really, really high frequencies. Apparently, there are some engineering limitations pala din, if not at least some associated energy cost or manufacturing cost in being able to produce something that can move at the speed that quick. So that one main source borrowed by lectures 3 to 5. Something like this apparently would hit the megahertz range, and yung sabi din daw, something like that would also be very costly to maintain. Pero as far as we're concerned, that's also strangely like the simplest form of modulator. There are, however, improvements naman. But first, let's also see kung ano yung parang behavior niya. Now, it turns out there's another parameter called slew. Yung capacitor daw sa circuit yung may kasalanan nito, and it somehow introduces some slowness when it comes to being able to transmit the signal. So there needs to be some trade-off between how large you're able to quantize your data and how fast you're able. There's a trade-off in designing as a result. No, you need to figure out the right balance between that capacitor lag, how big you're able to quantize, or rather how precise you're able to quantize your data, along with how fast you're able to make sense of that data. Now, it turns out there have been companies that have been working on solutions to that. Apparently, this solution was by Motorola, known as the continuously variable slope delta modulator. The underlying idea is that there's an added logic circuit meant to compensate for the slew rate. But even that has its limitations. As a result, there's another modification to that. Imbes na may logic circuit, paano kung yung value ng comparator, i-compare na lang siya against ground versus yung circuit proper. So this is the delta sigma converter. So yun nga, hindi siya slope dependent. And if anything, there's like a digital output. And this is unfortunately the limits of my knowledge. So let's try and move on naman to lecture 4. Sampling and aliasing. So what about aliasing ba? What exactly even is it? What even is an alias? Apparently alias is like a nickname. And I'm sorry, why is this surprisingly short? Yeah. So yung sampling theorem basically is kung maayos yung pag-sample mo daw, you should be able to reconstruct the analog signal. So kumbaga you have enough data na parang madali na lang yung fill in the blanks na gagawin mo. Unfortunately, yung kalaban nun is aliasing, and this is pretty much it. Yung sample mo, somehow, hindi niya na-represent ng maayos yung waveform na nabuo mo. That's basically what aliasing means. Now, yung sa left, hindi siya ganun kahalata. Pero, yung right, that would be a more clear example of what aliasing can do. So, to the right, makikita natin na grabe yung na mas mataas yung frequency dapat. Pero, yung nakuha nating waveform after sampling shows a frequency that's significantly lower. So how can this be? Unfortunately, that's really the consequences of sampling and quantization. So how can we get around this? Now, it turns out there's this thing we call the Nyquist sampling theorem. You can basically reconstruct the signal only if yung sampling rate mo is double that of yung pinakamataas na frequency na present sa signal. So take for example human hearing. We want to be able to reconstruct a waveform na at most would have 20,000 hertz. So as a result, yung gagawin nating sampling doon, kailangan doble nun. So sample rate natin would be 40,000 hertz. Though granted, yung common sample rate na ginagamit for sound files, surprisingly, is 44.1 kilohertz. Either way, yung implications ng Nyquist sampling theorem when it comes to that common practice is that the entire human range of hearing can be fully reconstructed with that 44.1 kilohertz sample rate. Kasi yung human hearing range of 20,000 hertz, pasok siya within 1/2 of yung sampling rate natin. So let's go back to the previous example. Kung mapapansin nyo, parang if yung spacing ng mga sample points natin, no, yung horizontal spacing, their spectra time, they're significantly larger compared to, say, yung actually no, hindi ko rin yun masasabi with regards sa left. Pero for the right, masasabi ko definitely yun na tipong yung wavelength, well no, yung period ng wave natin is super close to yung sample rate natin. So something curious is happening talaga. So yun. Again, Nyquist sampling theorem. If you're sampling a circuit, dapat yung highest frequency niya should be half the sampling rate. Pero how do we achieve that? This is basically the part where I'd ask for a brief break. Let me just add a few more slides and we'll get to filters. Filters are basically meant to accomplish that little problem, namely low-pass filters. Low-pass filters' main goal is to basically shut off those other higher frequencies. And it turns out not all filters perform the same. Some are basically able to remove higher frequencies better than others, especially those frequencies that are close to the cutoff frequency. So give me around 5 minutes and hopefully we should be able to start back again. For now, I'm just going to, for now I'll be muting myself while I prepare the last slide with the graphics. So for now, just feel free to draw. I hope you've gotten a screenshot, because I'm about to start sharing screen in 3, 2, 1. Granted, I'll also bring it back naman afterwards. So yun. As much as I have experience, ang problema, alanganin pa rin yung context eh. I know how to use MATLAB, but not for signal processing. So for sure, that's one of the other things I'll be doing next week now that we're practically cleared with the lectures, well, alongside the figure out your exam. If anything, kailangan ko nagulon pa rin si Sir Leo about additional references nga rin eh. But yes, yung context talaga namin as engineers when it comes to signals, it's within the realm of control systems in terms of being able to establish systems that are basically able to self-correct. Yung intricacies ng circuitry, we only have like a glimpse of it, but not the full picture. Yung pakialam namin mostly would be yung mga actuators and just whatever springs and dampers we have integrated to the system. Obviously, yung katumbas ng mga spring masses and dampers would be, I think, capacitors, I think, are, no, inductors ata yung katapat ng springs. Capacitors would be more of the damper. And yung pinaka-mass would be, I think, the resistor. But yeah, I'm trying to recall like the second order equation na katapat ng LRC circuits. Parang gano'n ata kung i-compare ko to a spring mass damper system. But yes, bottom line, the only overlap, one of the more familiar overlaps sa akin would be mentioned naman later within this lecture. So let's start off with filters, at least yung broad categories. So passive and active filters. Passive filters, panay mga passive elements. So yung mga capacitors, resistors, inductors, basically they don't actively respond to any change in either the current or the voltage, unlike active filters. At that point, you're now introducing transistors and op-amps na tipong hindi exactly pare-pareho yung behavior nila for a certain voltage or current. Like somehow voltage 1 behavior is different to voltage 2 behavior, just as much as current 1 behavior is different to current 2 behavior. And that said, there are curious things then when it comes to certain passive elements. Apparently, there's this fabled fourth type of passive element. It's a strange variation of the resistor. But you know, that's unfortunately beyond my purview. Something about it, parang it's able to somehow remember its own resistance. So I think third order. Not sure. So what about yung filter behavior? This is when we start looking at filters naman based off of frequency. The simplest case would be the low pass and high pass filters. But we can also put them into combination to create band passes and hindi ko na kung yung tamang graphics sa band pass pala. Band pass versus band stop. So basically band pass is the complement to band stop. Band pass, certain ranges of frequencies lang yung papasok. Band stop, it's the other way around. Surprisingly, we are able to accomplish something like this structural engineering by the right combination of springs and dampers. If anything, parang we use that in a lot of machines para medyo calm siya. More often than not, we'd have a loose idea na, ito yung frequency na grabe siya magalog. So we put in the right set of passive elements to somehow kill off that frequency response. Unfortunately, that comes with its interesting quirks. Kagaya ng kinakwento ko, parang I think, I'm not sure if it was yesterday or the other week, something about introducing an element wherein its resonant frequency matches that of the original thing, ends up splitting it into two peaks that are incidentally sharper. The behavior when it comes to circuitry, unfortunately, is something that's lost to me. So I'm not quite sure kung paano yung analogy. So it turns out, common filters na ginagamit sa analog signals are the Chebyshev, Butterworth, and Bessel filter. Although the Bessel filter is also called the Thompson filter. So apparently yung pinakamaganda sa kanilang lahat would be the Chebyshev filter. So one example lang of a Bessel filter. More often than not, low pass. 6 poles siya. So those poles are basically a consequence of yung mga passive elements niya. The poles have something to do with those resistors and the poles basically have something to do with the very block diagram that can be associated with this circuit. So we're bound to get to that later down the line. Now, here's the thing. When it comes to circuitry, the trend is miniaturization. It turns out you're not able to do that properly with a resistor. So rather, pagdating daw sa mga RC filters, rather than using a bulky resistor in conjunction with a capacitor, paano kung yung resistor, palitan mo na lang ng rapid switch? So apparently that's the so-called switch capacitor filter. You're able to basically make that switch in silicon as opposed to the classical resistor capacitor circuit. Now, let's actually move on to one critical property of filters. So apparently there's what we call cutoff sharpness. Ito yung sinasabi ko na gano'ng katanda siya mag-dampen at the moment na nagsisimula na yung fall-off. Yung pinaka-ideal kasi, pagka nandun ka na sa cutoff frequency mo, anything after that, putol na. In my times with having played with audio, that's easy. Pero yun nga, digitized na yung signal and basically na Fourier transform yung samples. At that point, the necessary math was done to be able to filter out yung higher frequencies. Pero let's say you don't have that liberty of having the signal digitally processed then reconstructed as an analog signal. Gusto mo purely with an analog na ma-process na kaagad. Well, here's the thing. Ideally, we want something like this, no? Itong sharp drop. But in the real world, we end up with something like this. So this is the performance of your Bessel filter when it comes to cutoff. Well, roll-off, as it's also called. Apparently, the more poles you add, the better the behavior becomes. So let's try and take it a step up. Tingnan naman natin yung nangyayari with the Butterworth filter. Turns out, medyo mas maganda yung performance niya when it comes to cutoff. Still not good, but significantly better compared kay Bessel. But what about Chebyshev? So Chebyshev apparently is the best filter, pero there's something very unusual when we're looking at the linear scale ng filter. So it turns out, sa band na tinatanggap ng filter, nag-ripple siya. And if anything, I can even tell you of a very unusual characteristic in my other fields of exposure. What's up with that? What's up with that ripple? Thankfully, mababa lang yung percentage nun. Thankfully, parang as much as it might be noise, it's very, very minuscule with respect to the absolute waveform. If anything, for it to be able to achieve that sharp cutoff, that's the necessary sacrifice it needs to make. Now, additional characteristics when it comes to your filters would be step response. So, how does our filter respond kapag magkakaroon tayo ng input change? If anything, ito na rin yung familiar sa amin pagdating sa control systems. At least, mapa-physical or digital. I mean electronic, but we're more within the realm of physical. So, two core things would be overshoot and ringing. Overshoot is basically gano'ng kagrabe siya lumampas. This is present when your system is underdamped, as we would call it. There's also ringing, which is also present in underdamped systems. More often than not, with your systems, parang there's like three critical categories of damping. Underdamped, dun mangyayari yung ringing and overshoot. Critically damped, parang mangyayari sa kanya, hindi siya mag-ring, hindi rin siya mag-overshoot. If anything, parang halos kaagad siya mag-respond with respect sa signal. Pero parang may pa-arte pa rin na log. And then meron din yung overdamping wherein hindi siya mag-overshoot, hindi siya mag-ring, pero it's slower than it should be. Common practice sa amin as mechanical engineers is to go for a slightly underdamped system. So try and reach a point wherein the system is designed to be as close to its critical damping with a slight leeway. Parang yung katumbas din nun, minimized yung overshoot. But for filters, the situation is very different. So let's go over the response of our common filters, starting off with the Bessel response. This, I'd say, would be an example of, I'd like to say underdamped, as I'm seeing like a slight nudge along the amplitude. May slight na overshoot siya. So yun, parang critically overdamped example. This would be if this is not a critically damped example, this would be close to slightly underdamped, if not slightly overdamped. I'd say 4 would be your example of a critically damped system. 8-pole yung parang magiging overdamped, and then 2-pole yung magiging underdamped. Butterworth, lahat ng response niya happened to be underdamped, given yung yung napapakita niyang overshoot and oscillation. Pero, just as with control systems din, parang kung hindi na grabe yung, you're going to find that point wherein yung pag-change ng yung pag-oscillate niya is not that grave. If I recall, parang I think it's called settling time. More often than not, the more critically damped the closer your system is to being critically damped, the shorter that settling time tends to be. And parang there's like an associated time to it based off of the system parameters. So let's try and compare naman din the Chebyshev filter, at least one with a 6% ripple. So, yun nga. Akala natin na porque maganda yung cutoff ni Chebyshev. Unfortunately, when it comes to its step response, medyo wild siya pagdating sa oscillations and overshooting. So you'll have to choose wisely kung anong filter ang kailangan mo based off of yung application. Paano basahin yung table? Amplitude versus time? Or amplitude versus frequency? Overshoot and ringing, more often than not talaga magsasabay yung dalawang yun. So, balikan natin siguro yung example ng Butterworth. Sabihin natin yung, actually hindi to impulse, sabihin natin yung units, yung step input natin, target niya is 1. Yung overshoot part is basically gano'ng kagrabe siya lumalampas from 1, from yung starting point niya na 0. So parang everything slightly above 1, yung overshoot part niya. Yung pinakamalaking distance from the moment na nag-step input ka, yun yung overshoot. Yun yung magiging degree of overshoot niya. So sabihin natin, let me just create a pen. Yes. So let's track siguro yung 8-pole example natin. Itong amplitude na to would be corresponding to yung overshoot niya. Whereas, yung ringing niya would be basically from this point na natamaan niya yung target value all the way up to yung settling time niya na hindi na siya ganun kahalata. I think it would be this. I'll have to counter-check my notes when it comes to control systems. Pero I think such details naman should also be present in your books. Bottom line, overshoot usually comes hand in hand with ringing. And as much as possible, you want to shrink that overshoot and ringing. Actually, itong kwan ko would be the settling time. So parang that's how long it rings. So yan, grabe si Chebyshev pagdating sa ringing, pero ang ganda ng kanyang cutoff. Now, there's also the matter of how quickly you can respond. So ito yung naabutan ako ng time bago magklase. So si Betzel filter, it turns out, as much as napakapangit niya when it comes to cutoff, ang ganda niya when it comes to response. Kasi tingnan mo, ang linis niya. Kung meron siyang overshoot, halos negligible siya along the amplitude. Tapos kung may ringing din siya, sandali lang. Compare mo siya kay Chebyshev. Ang ganda niya mag-cut off, pero hindi siya kalmado when it comes to yung ringing niya, let alone yung overshoot. So at the end of the day, you'll need to figure out what application your circuit will be part of. If you need to prioritize response characteristic versus its capacity to filter out frequencies. And that's basically the coverage of the preliminaries. Next week is free unless you'd like to try and practice on some of the practice problems. Sige, practice tayo. Actually, we can probably try practicing some of the sample problems right now. We have a two naman din eh. I'll just start logging lang. Kasi at this point, parang I'll just start taking names. Okay. So siguro we have like 2 hours naman to try with the sample problems Canvas. So maybe I can try and load that up right now. Okay, give me a moment. As far as we're concerned, I've already logged yung attendance for the lecture part. So yun, we can end now or yeah, let's try and practice now. 2 hours pa naman eh. Okay, give me a moment. I'll just end screen share and prepare uploading some pictures. Try natin siguro i-follow yung nasa module 2. Right. The solutions naman are present in the module, pero siguro we can try and go through it kung ano nangyari. I think this is like the heart, no, among the later examples. So let me change to something slightly easier. Also, ano yung kinaganda ng cutoff or yung use case niya? At the end of the day, Sir Eric, you'll need to figure out that in the field. Kasi depending on kung ano yung kailangan mo sa signal, sometimes mas importante yung cutoff. Sometimes mas importante yung step response. So siguro kung actually hindi rin eh. I don't think I have enough context to figure out such cases. At the end of the day, yun nga talaga eh. It depends on the very system needing it. So unfortunately, I really cannot give you a solid answer. I guess one thing na maisip ko, let's say for the case of resonance, you're actively trying to stop certain vibrations. Or more, no, let's try and bring it to your context of electrical circuits. Sabihin natin, yung pinaka-circuitry mo happens to be vulnerable to a certain frequency. So parang ang gusto mo mangyari doon, kailangan somehow mawala yung frequency na magbibigay ng problema. So at that point, yung gusto mo mangyari would be cut off. Pero sabihin natin, wala ka masyadong pakialam kung hindi niya ma-silence out yung frequency. Ang gusto mo lang mangyari, kapag in-on mo na, kapag ka nag-turn on ka, kaagad dapat mag-turn on at hindi siya lalampas basta-basta. Hindi at that point, yung step response yung pakialam mo. So again, I cannot overstate na it really depends on the case of what's more important at the time. Okay, now, how do I change? Alam ko nagawa ko na ito dati, yung pag-swap out with the presentations. There we are. Siguro let's start off with this one. Consider the unit step function. Well, consider this signal. Now, ano yung magiging itsura nito if you express it as an equation using yung step functions natin? So yung convention apparently, kapag unit step function, we're going to use U. Tapos kapag impulse, we use D, or more rather yung maarting D meant to indicate partial. And then kapag ramp function naman, R. So go. Bear in mind din yung magnitude natin. So you'll also need to indicate that in terms of your step functions. Don't forget the offsetting din. Remember, with how our functions are defined, an impulse function is undefined at zero. Pero yung area niya is sort of like yung property na makukuha sa kanya. Tapos there's also the notion din of offsetting. So meron kayong moments in time kung kailan siya mag-offset. Meron kayong amplitude. Write the equation. Man, it's been 10 minutes. Hindi niyo ma-visualize? And I did say I'm going to give some hints. So, yung unang hint na masasabi ko, panay mga unit step functions to. One positive, one negative. Meron naman kayong whiteboard input, pero pwede naman din in public chat yung sagot. One or the other. So this is basically like at least two step functions. I have to turn my head at an uncomfortable angle, pero tama. So, bali yung 10ut minus 2, ito yung part na yun. Hold on. Color code ko yung highlights. Using red ink would be stupid. So, itong part na to corresponds to itong bit na to. Yung t minus 2, yan yung offset niya. Pero, yung drop, paano naman yan? That's basically where the other part came in. Yung 10u t minus 5. Yung t minus 5 yung offset niya. Pero, yung negative 10, yan naman yung amplitude niya. Leading to, so parang mangyayari, ganito yung, yeah, parang ganito yung 10ut minus 5 natin. Kapag nag-add up yung dalawang yan, ito yung lalabas. So, tama. Okay. Let's move on siguro to another one. Panay impulse functions. Whiteboard. It's gonna be hard kung sa GC. I'd rather dito sana sa one. So, solve for the equation just like before. Lime green is probably the worst color of ink. In hindsight, dapat pala siguro ito yung inuna ko. Impulse functions kasi when it comes to yung, yun nga, just revisiting my story when it comes to my exposure to impulse functions. We've normally used that in terms of beam analysis. Impulse functions normally correspond to points along a beam wherein a certain amount of force is applied. Yung strength ng impulse basically corresponds to some force applied. So, bale kung negative siya or positive, bale up or down yung force. Pero there have been cases wherein, rather than at a single point of application siya, parang it's over a particular area of force is applied. Yan yung parang naging katapat namin to step function, tama, step functions. And sometimes, may katapat kami to ramp functions. Although in hindsight, apparently yung nasa group chat is practically the answer. But like you could see naman how yung second item is why as to why that's the answer, di ba? Kasi yung impulse natin occurs at time equals 2. And then yung second impulse natin is at time equals 5. Likewise, yung parang na-imply na strength sa ng impulse function natin would be 10. So parang yung unang impulse natin is 10 and then yung next impulse is 10. So that's basically it. I guess we can actually move on to the ramp function. So let's try and use this one. Apparently this is up to 3 functions combined. So dalawang ramp plus probably one step impulse. Yeah, dalawang ramp and one step unit step function. So solve. Siguro before we end the class, actually I'm going to see if I can add that one picture muna. So chances are baka maputol yung attempt nyo habang nagsasolve. So pardon me for a bit. Okay, meron na tayong paglalaroan mamaya. Okay, back to yung ramp na to. Okay, sige. We can solve this together. At the end of the day, in solving signals by decomposing them kasi into input functions, you basically need to figure out kung paano mo siya i-decompose. Now, itong example kasi na to, it's also present naman din in the modules handed over to me. So, let's follow the module step by step. So, first things first. Yung nakikita na natin kaagad, sigurado tayo there's like at least one ramp function. So, yan yung ramp na to. Pero, yung makukuha natin na first part would basically be this ramp. So, ano yung equation nito? So, for starters, alam natin, nagsisimula siya at time equals 0. So, yung unang mangyari, yung sigurado natin so far, kwan pa lang to, R of t. Pero, here's the next problem. Yung kailangan at time equals 2, yung ramp natin equals 10. So, hindi lang siya simple u of t. So, ano yung pwede natin i-multiply sa u of t natin? Kung sabihin natin r of t, I'm sorry. This is not simply r of t. So, anong mangyayari para pumalo siya ng 10 at t equals 2? So, kung babalikan natin yung definition ng ramp function natin, we need to give it an amplitude. Hindi lang siya basta-basta per unit. Kailangan na amplitude siya. So, paano kung sabihin natin times 5 natin siya? Will our ramp function satisfy that? So, bale, at time equals 2, r of t equals 10. It turns out, kung r of 2, ang mangyayari, kung r of 2 lang siya, yung v of t natin ultimately becomes 2. So, kulang yun. Pero may ratio tayo sa kulang. 10 over yung 2 kung r of 2 lang. Makukuha natin yung multiplier natin. So, yung multiplier natin would therefore be 5. As a result, yung unang component natin would be wow, okay. Nakikita niyo ba yung parang alanganin ni masyado kung light blue yung gamitin ko, no? So, let's use this blue. As a result, yung unang part natin is 5 RT. Yan siya. Next, kailangan natin ipabagsak siya. Pero it turns out, hindi rin natin yan basta-basta pwede ma-flatline. So the next thing we need to, so how will we go about this? Yung next na pwede natin gawin at the very least is to start, yun nga, hindi natin siya basta-basta pwede ipabagsak. Pero that would be the next step siguro. So how would that, paano kaya? Ano yung pwede natin idagdag muna? At ano yung magiging itsura niya? Sabihin natin, itong bit na to, may katumbas kasi siya na step function. Conversely, pwede rin natin siya i-deconstruct na i-slant siya pababa para kapag magdagdag sila, flat siya. So anong gusto niyong unahin? Bring 5RT down or flatten 5RT? Guys, anong gusto niyong unahin natin muna? Ipabagsak yung ramp or i-flatten yung ramp? Oh wait, hindi siya nagsuscroll. Down, okay. So, pabagsak daw natin si RAM. Ang expected na magiging itsura niya would be something like this. Kailangan natin na-generate itong segment na to. So, paano pwede natin gawin dyan? Sigurado tayo, yung isang part niya, obviously, is yung 5RT. Pero, meron pa tong dagdag. Or rather, meron siyang bawas. Now, it turns out, ang bawas niya, unfortunately, hindi ko mapaportray yung scale niya. Meron tayong step function. Actually, no, dapat ibahin ko yung tinta. There you are. Meron tayong step function na kailangan i-dagdag dyan. And if anything, this is definitely not to scale. Itong step function na to, meron siyang amplitude at time equals t. So siguro na doon na tayo na we need to offset our step function. So kagad yung nasa loob na nito is u of t minus 2. Pero meron din tayong amplitude na kailangan habulin, which happens to be 10, para mapabagsak natin yung ramp function natin all the way to the bottom. So turns out, itong step function natin would be 10 u t minus 2. As a result, itong panibagong signal natin so far would be 5RT minus 10 u t minus 2. Oops, bakit ko na type 1? That's curious. So that's the second step. Ngayon, gusto natin mangyari, i-flatten yung signal ng todo. So basically want that to happen para completely solved. So just like before, this new one basically copies yung nauna na dati. So bale, this is still 5RT minus 10 ut minus 2. Meron pa tayong kailangan idagdag dyan, or rather, bawas ulit. This time around, it's going to be a ramp function. So, kailangan natin makancel yung 5RT sa part na to. Pero, ayaw din natin yan mag-start kaagad. So, ultimately, yung idadagdag natin, as paggrabe ng paggrabe yung illustration ko. Let's see. Let's try green. Kailangan, meron tayong itong green na ramp function. So itong green ramp natin, yung slope lang niya is basically the same as our previous one. Pero, this time, we also need to offset it. So, yung magsisimula siya at t equals 2. As a result, yung panibagong ramp natin is -5 ramp t minus 2. Oh yeah, a bit of a typo pala. I forgot to add minus sa amplitude ng step function. So, kapag in-add natin siya sa itong wave part na to, yung buong solution natin as a result becomes this. So that's basically reconstructing the equation from the graph. I could end the class here na, pero what about the reverse? So siguro screenshot nyo yan. I'm about to change this to a blank grid in 5, 4, 3, 2, 1. Okay, this time gusto ko, kayo naman bumuo ng signal nyo. So siguro someone suggest an equation based sa limits natin. So hanggang v of t equals 3.5 tayo. And then hanggang t equals 6 tayo. Yung mga dots lang na yan, I just use them to generate. They're not necessary. But no one's stopping you from using them for creating your function. So someone type sa group chat or input na lang into the board kung anong function ang gusto niyong buuin. Pero at least 3 parts dapat siya. So yeah, and no negative values because apparently I didn't have enough foresight to plot. Sorry. Gusto niyo ako na lang magbigay ng function na kailangan niyo i-illustrate? Okay, sige, sabi niyo. Kung gano'n, actually hindi. Kung i-type kong mapuputol siya. Type ko na lang siya sa group chat. Yung assumption pa rin natin, horizontal axis natin would be t, and then yung vertical axis is some arbitrary value of amplitude. Sabihin natin voltage ulit. So far, yung na-illustrate nyo is not a ramp function but a step function. Sige, I'll give the first stroke. So remember, ramp function, slope ang naka-specify doon. So bale at t equals 0, exactly 0 siya. At t equals 1 of a unit ramp function, equals siya to 1. So at t equals 2, yung ramp function natin is equal to 2. Yun, you've basically illustrated r of t, and that's the first step. Pero, yung next step, paano naman yung 2rt minus 1? So, yung sinasabi ng second part, at t equals 1, magsisimula na siya. Tapos, yung kanyang slope is negative 2. Pero meron ka ng isang ramp function na slope equals 1. So, bale, 1 minus 2, mangyayari, negative 2. Mali tong bridge na to. So far, tama yung yellow. Pero hanggang 1 lang siya tama. Yung next step is, kailangan mo na i-take into account yung 2rt minus 1. So yung mangyayari, at t equals 1, mali yung orange. At t equals 1, yung slope naman niya this time around is minus 1. Kasi meron kang plus 1 na slope, and then nagdagdag ka pa ng minus 2 na slope. So at t equals 1, pababa na siya from wherever its current point is. So kung sino yung nag-drawing ng yellow, kindly correct that. Siguro i-kuan mo na lang siya up to 1 kasi hanggang dun lang yung sigurado. At t equals 2, mali na yung yellow line eh. Yun. So next part, yung r of t and minus 2rt minus 1. So bale, from that point, kailangan bababa siya with a slope of negative 1 hanggang yung next point na kailangan natin pakialaman. By the way, with regards pala to our prior discussion of filters and their response, you can expect na if you're going to have a machine that tracks that, depending on your filter, either also mali yung sudden drop down, hindi siya ganyan ka-sharp. Yung nangyari with that is more of a step function. Kailangan yung ramp yung ma-account for. Now, where was I? Yung filters. So, medyo ma-imagine nyo. Kung yung, ano ba? Yung isang filter, man, dun yung sa slides kanina lang. Yung maganda yung kanyang step response, pero alanganin yung filtering yung powers niya. That roll-off, yung cut-off characteristics yung alanganin. You can expect na mas maganda yung pag-track niya dito. Si Chebyshev nag-stand out kasi ang napakalaya ng pangalan niya. And then of course yung filter ni Thompson, yan yung parang best of both worlds. So you can imagine yung Chebyshev filter kung sabihin natin, in-execute natin. Kung tatry niya i-track yung line na yan, parang slight lag pero grabe. Expect na mabilis siya mag-follow up hanggang dito. Kapag ma-draw niya yung next line, si Chebyshev parang lalampas siya for a bit and then hahabol ulit. Yun. Okay, good. So that's the entire thing from up to t minus, from that's so far the entire function hanggang t equals 2. Now, ang kailangan ko is up to t of 6 and meron pa tayong isa pang component na hindi natin na-take into account. Plus rt minus 2. So far, yung slope natin is negative, oops, mali na yung purple. So far, yung slope natin is negative 1. Pero yung panibagong ramp natin, nagdagdag tayo ulit ng 1 sa slope. So as a result, yung slope natin is now 0. So ano yung implication nun? Yes. And all the way up to 6 na yan. Now, here's what I reckon. Ito ata yung magiging exercises natin when we start playing with MATLAB pagka mag face-to-face tayo. as much as sabi ni Sir Leo na may experience ako sa MATLAB, he's correct. Pero I don't think he fully mentioned na my experience is strictly limited within the context of Gem 5. So again, yung experience ko in the suite is currently limited. And for sure, I'll do my due diligence to study it throughout the next week, along with drafting your exams para, yun nga, face-to-face and all that. Although sometimes iniisip ko rin sana sa last day of face-to-face magpa-pizza ako. Oh well, depende na lang kung kaya ng sahod. So, yun. Gusto niyo parang isa pang example or end class na? Well, to be fair, nag-lunch na ba kayo or hindi pa? Maybe we can end na, no? I think we've practiced enough. Oh, okay. Binigatan nyo ba yung almusal nyo? Or nagla-lunch na kayo habang nagkaklase? Sige. So maybe we can try... Sige. So I guess maybe we can meet for one more time next week during the lab hours, maybe for 1 to 2 hours. We could probably try 2 problems ulit na class generated para meron kayong grasp kung paano i-generate yung functions. So bale, one na solve yung function, i-describe yung function galing sa graph, and then isa ulit na create the graph based off of the function. With that, let me just log everyone one last time and then dismiss ko na kayo. Unfortunately, the next topics ang mas weird eh. These are the topics that lean more heavily onto math na hindi ganun kasimple i-drawing. So, we're all going to study in this. You are students and I as the lecturer. Pero at the same time, I'm planning baka gawin kong group reports kasi kulang na ako sa context. So, we have like what? 2 weeks pa naman to figure out kung group reports on modules or ako pa rin. And I'm really leaning on to group reports kasi you as students within the field can definitely bring more context than I ever can. Siguro sana naman by the exam I can make my mind up para finalize na kung anong mangyayari for midterms and finals. With everyone logged, i-dismiss ko na kayo. So siguro take another screenshot as soon as I save this. I'm going to start a countdown and then end ko na yung session. Kayo. Hindi ko na yan i-erase.